Here's what we're going to aim to do today. We're going to cover the closest pair of points algorithm a little bit more carefully. Then we're going to talk about another problem called arbitrage. It's also a divide and conquer algorithm, and it'll use a technique that will come very useful in solving the homework problems. Okay, let's get started with closest pair of points. So let me set the problem again. Remember, we're given n points in the plane, and we would like to find the pair that is the closest. It's a natural problem that arises in many problems like graphic simulations, economic problems, geometric algorithms, etc. The brute force algorithm, if we take every point and compare it to all its neighbors, that would basically take n squared. N comparisons, n minus 1 comparisons, n minus 2 comparisons, etc. That would sum to n squared. So we're looking for a better algorithm for finding the closest pair. We're studying a technique, taking a problem on an instance of size n and dividing it into a smaller problem, in particular the same problem on inputs of size n over 2, and then somehow combining the solutions to those different type of problems. That's the idea and the technique. When you start your homework, I want you to think in the same way, not an ad hoc way of, well, let me think about recursing all the way to the bottoms. Think about systematically in exactly this way. So we have n set of points. We can divide this problem easily into two problems just by drawing a line smack in the middle. So we have n over 2 points on the left and n over 2 points on the right. The points on the left happen to be exactly the same instance as the big problem, right? Let's find the closest pair of points that happen to be on the left side. And similarly, let's find the closest pair of points that happen to be on the right side. It's the same exact problem, just smaller. And now we know that essentially the solution to the problem is either going to be this pair right here, or it's going to be a Romeo and Juliet pair, where one point is on this side of the left side and another point is on the right side. So that is the divide and conquer. We divided it into one half and another half, and then we're going to combine these results by just checking for the extra case of this Romeo and Juliet. What was our insight there? So let's say we found this pair and it was separated by delta, and let's say this pair was separated by delta prime larger than delta. And now, when we need to look for these Romeo and Juliet pairs, our insight was that we know that such Romeo and Juliet pairs have to be within delta units of our middle line. And so we have a nice mohawk where we know that the answer of Romeo and Juliet has to be right here in this middle section. That was our first observation about this problem. Each of these homework problems will be just like this. You'll make a series of observations that you'll have to then overcome the next hurdle. So now the next hurdle in this problem is that although we know that our Romeo and Juliet have to be in the mohawk can actually have lots of points in it. But the point I want to make, the next hurdle that we're going to overcome, is that the mohawk can contain all of our n points. So we can't just rely on some argument like, well, the mohawk is going to have a constant number of points, and so we can just exhaustively test them all. That won't work because in this case, exhaustively testing all of these n points would lead us right back to the n squared algorithm we're trying to escape from. Our next observation was that we can take our mohawk, we can divide it into cubbies that are of size delta over 2 by delta over 2. What we do is we find the point that's at the bottom y coordinate, and we start our cubby line right there, and we use that line and this line right here to define a grid, a delta over 2 by delta over 2 grid. And why did we do this? There can only be one, like the Highlander. We know that the cubby is delta over 2 by delta over 2, so if we had some point at the extreme left corner of this cubby, the farthest point will be the extreme right cubby, and that's going to be, by our Pythagorean theorem, square root of 2 over 2, which happens to be less than delta. And so because we know that left points can only be separated by, have to be separated by more than delta, we know that each cubby can only have 1 point. Question. So we know that cubbies have at most 1 point. And this is our second major insight. How can we exploit this? Well, then comes that geometric packing argument that I made. Take a look at this bottommost cubby, and imagine putting a circle of radius delta right here at these four corners of this cubby. We know that our Juliet has to be covered by a yellow box. And so if we just draw all four of these, this gives us a list of boxes that we have to look at for Juliet. I'm going to go do another example right here, the red dot. If we draw our yellow circles of radius delta around that box, then we count the number. By this simple argument, you can easily count that it has to be less than 15. Now, you can make a smarter argument. You can make the bucket slightly different size, and I've seen analysis where you can actually show that you only need to check 7 buckets. But let's not make a complicated analysis of this. All that matters right now is that from this particular bucket, I only need to check the next 15 buckets to look for Juliet. Question in the back.
Why don't you only need to check buckets on the other side of the line?
As I've said, we can do a better analysis on this. But I don't want to. The algorithm I'm going to show you doesn't need to distinguish to whether the point is on the left or the right side. It's just going to check the next 15 points in a sorted list. That's going to make the implementation easy. It's going to make it so that I can show you all of the code on a single page. But you are right that a faster version of this algorithm can actually use a fewer number of buckets, can check a fewer number of buckets. Question. We don't know where the point is. All we know is it's in the cubby. It's somewhere in the cubby, so let's consider the worst cases. Those are the four corners of that cubby. This is an argument to say no matter where the point is in the cubby, I only need to check my 15 neighbors of that cubby. Question?
Yes.
Okay, so this circle might not be to scale, and it might exactly touch a little bit of that. And again, this is one of those questions where, yes, from 15 we might go to 12 because we don't need to check that top row and so forth. But as a very simple argument, there are only 16 boxes, and so if I check those, at least it's a very good bet. But yes, I can give you pointers to do a more sophisticated argument where we only check a smaller set of buckets. Question. For each bucket, for each point, a point is in a bucket. For that point, I'm going to look at the next 15 buckets. And I'm going to give you some pseudocode in a second. What I'm actually going to do is sort all of the points in my Mohawk by their y-coordinate. And then I'm going to take that, I'm just going to go to the next point and then check the next 15 buckets. In fact, let me do that right now. 1 second, I see your question in the back. The algorithm is going to work as follows. We have our Mohawk, we have all the points in our Mohawk, and we've sorted them by y-coordinates. So 1, 2, 3, 4, 5, 6, 7, 8, right? This would be 1, 2, 3, 4, 5, 6, 7, 8, etc. And what we're going to do is start with the first one and then just check the next 15 points that are there. This is again an overkill because in this case, for example, only 8 are in the next 15 buckets. The ones I check up here cannot possibly be Juliet's. Okay? But because we're going to use a very simple data structure, in particular a sorted array, all we're going to do is say we know that each bucket only has a point, and so the next 15 points have to be in 15 different buckets, and so it's good enough to just check the next 15 points. Question? Yeah, and technically all we're going to do is check against this point, so we have a sorted list right here. So we're at this point, we're going to check against this one, this one, this one, this one, this. We're going to check against the next 15 points in our list, which can actually go beyond buckets. But the point is we know that it contains at least, it will cover at least the first 15 buckets. So our algorithm is going to be loose in many ways, but it'll be correct and easy to analyze. Question in the back. So we're going to start at the bottom and work our way to the top. And so when I come to this point, I no longer need to check anything below it because When I was at that point below it, I already checked to see if this guy was my buddy or not. So we only need to check, we only need to look forward in life there. No regrets.
How do we come up with 15 then versus a lower number? Maybe that gets back to the initial problem.
Yeah, so take a look at this. Take a look at this box right here. So that number 15 comes from this diagram right here. I took this red point and I put yellow circles at each of the corners. And then I counted the number of boxes that are covered by this. And by a very simple picture proof, you see that there are only 16 boxes in this entire list, right? And I don't need to check my own bucket because I only need to check 15 boxes. That's how we get 15. The number 15 doesn't matter. If it was 60, it would still be fine. It just needs to be a constant. Because now all we need to do is say, take all the points in the Mohawk, there are at most n of them. For each of those points, I only need to check 15 friends. So that's still O of n time. Question in the back. These top rows? Yes. So the third time I'm going to say this. The diagram is not to scale. One can do a better analysis. And in this case, you see this circle just barely touches that. So why not cover it? I don't want to make a tricky argument to say this is like a strictly less, the bubble is strictly less than. So as an upper bound, 15 will be correct. And as I've said, there's a better analysis to get 7, where you can just check the points on the right, like 1, 2, 3, 4, 5, 6, and then possibly that one's 7. One can do a better analysis, but I'm not going to do it here. Question? Yes. Yes. Notice that the delta by delta over 2, that doesn't have anything to do with 15, right? Essentially, it's this over 2 factor that gets you to 15, that gets you to 16. This over 2 helps you do this type of diagram, right? Because this circle is of radius delta, and this side is of length delta over 2. So you can sort of see that there's a delta over 2, a delta over 2, a delta over 2, a delta over 2, and that's going to cover like roughly. More questions? You had one more.
Yeah, we can ask that same.
Does anybody feel it could be more than 15? So it's at most 15, right? So that's all we need to get a linear time algorithm. Raise your hand if you're puzzled why it's not 7. If it was 100 or 1,000, it would still be constant time. So when you are making your algorithms, don't fall into the trap of optimizing this. We're not in a let's write assembly contest and get the fastest algorithm business. We're not in that. That's not this class. We are looking for simple and clean arguments, so don't over-optimize these things. Optimize for simplicity. Okay, so this is what I want to do. I want to sort of go through how let's say this was a homework. You had to write an algorithm, and now you all have the instinct of what the algorithm is. Well, we divide the points into 2. We split and we compute the left and the right closest pair. We compare their distances. We find the smaller one. Then we make the Mohawk. Then we analyze the Mohawk. Okay? That's in your head at this point in class, I hope. Let's try to write it down. Okay, so the closest pair of points, and this is going to be all our input points. So base case, if the size of P is like less than 2, let's say, do brute force. Otherwise, first 3 steps. We compute the midpoint along the x-coordinate. That's so we can draw that middle line. Then we split the points into left and right halves according to this Q. And now we basically say delta L is equal to the closest on the left. Delta R is equal to closest on the right. Okay? And then we let delta equal the min of delta L and delta R. So then we define M to be the mohawk around point Q. So those are all the set of points that are within delta units of Q of X. So if your X coordinate is within delta of that mohawk, you're in this set M. For all points, Romeo in M, sorted according to Y coordinate, check next 15 points. If the distance between Romeo and Juliet is less than delta, set delta to how about this? We can write this even more compactly. Delta is equal to the min of delta comma distance between Romeo and Juliet. Last line, return delta. Question?
Earlier you said you have to have n over 2 points inside. Does that have to be true?
Let's get to that in 1 second. The answer is yes, because when we analyze the running time of this algorithm, we're going to need that fact. So I just have a better version of that same thing on the left. And now let's get to your point exactly. Let's do a running time analysis. Okay, so this right here this is what I need. If this is our algorithm, and we can compute steps 1 and 2 in order n time, notice that this right here, closest of left, this is of size n over 2, and this is of size n over 2. So this step right here takes 2 times t of n over 2. And to answer your question, this is why left and right have to be exactly n over 2 or roughly n over 2. The mohawk just means scanning the points. That takes order n. And then as we argued back here, if we just scan all the points in the mohawk, and for each point we only look at the next 15 neighbors, then this loop is also going to take order n. And you noticed why I don't want to use a more clever data structure that only checks on the left or the right side. This loop right here is very easy to write. And so as a result, it's the choice I made. Okay? So adding up all of this runtime, we get that t of n is 2 times t of n over 2 plus theta n. And by Master's theorem, that means that t of n is theta of n log n. Question. What I want to show in this slide, the point I want to show in this slide is that the answer to many of these divide and conquer algorithms that are n log n have this form. They're going to divide the problem into 2 and then spend a lot of steps that may take order n time that allow you to glue the answers together. At a high level, this is just like what merge sort is doing, just doing different things, but it's the same structure. What I wanted to do in these last 2 examples is give you an example of how to write your algorithm and then how to analyze the algorithm. Now, as you pointed out, there are a few problems with this solution. So The first, how do I do step 1? Instead of getting to step 5, let's just start at step 1. Let Q be the middle element of the points, where they're given to me like this. And so how do I find the middle point? How do I draw this line right here that was so easy for me as a human to draw? That's problem 1. A question? Okay, answer.
Yeah, so you could count the number of points on either side, median strategy, and then
Good, okay. So median is going to be one of those problems. It's a recursive algorithm that we're going to study either Thursday or Tuesday, depending on the time gods. We're not going to use that right now. So there is an order and median time algorithm which one could use for this problem. What we're going to do instead this is an idea, which is that we're going to, there are 2 ideas that I want to present in class today, aside from the 2 high-level ideas. One is give your algorithm slightly more information from the outside, and your algorithm might be able to exploit it as it does its work. Okay? And the next algorithm, the next step is going to be the opposite. Let your algorithm give you more information. The arbitrage example is going to reflect that idea. In this case, what we're going to do, before we start our divide and conquer algorithm, before we do anything, we're going to sort all the points in X order. So there we get 13, 1, 5, 14, 9, etc. We're also going to sort all the points in Y order. Okay? So the first, once we have a sorted X and a sorted Y list, then it's very easy to compute the middle point in this step. And in the next recursive step, right, we know that the points are right here. It's also very easy to draw the line. So having a list of sorted points in X order can really help you do that first step of the algorithm. How do we accomplish that? Well, we're going to write a wrapper around this program. The closest pair thing is first going to compute the sorted order in Sx, compute this in Sy, and then it's going to call that function that I wrote over there, the closest of P. So this, by merge sort, this takes order n log n, and this takes order n log n, and this takes order n log n. So the overall solution is still theta of n log n. I haven't asymptotically changed the work that I had to do. Now, our new algorithm is going to look like this. It's going to take in the point and these sorted lists. So then now this step right here can actually be done in order 1 time. We just have to index into the middle of the array. This step, as before, still takes order n time. We just scan the input and check whether it's on the left or the right side of x, of q of x, right here, right? And now, because our algorithm now expects a sorted list in x and a sorted list in y, we have a new complication, which is how to compute Lx, Ly, Rx, and Ry. The list Lx is going to be left points sorted, okay? Ly is going to be left points sorted by y, and similarly Rx and Ry. We start with all of the points sorted Sx and Sy, right? So let's take a look at that diagram. Right, this is going to be Sx and Sy, and now we need to compute 4 sets, right? We need to compute Lx and Ly, and we need to compute Rx and Ry. This right here is going to be Lx. This right here is going to be Rx. Now, how do we do Ly? Because notice these points right here are 6, 5, 12, 11, etc., etc. See, notice we go right, left, right, 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 left, left. So Here's what we do in order n time. We start with this point, and we know that this is QX, right? We just scan this list right here, and we start a list. Let's call it LY and RY. And we do the algorithm I love, which is you keep a pointer on the first thing and move that pointer all the way across the array. So 6 happens to be on the right side of QX, so we'll write 6 down. And then 5 happens to be on the left side, so we'll write 5 down. And then 12 is on the right, so we'll write 12 here. And then 11, and then 10, and then 3, 13, 4, 9, 8, 7, 2, 1, 14. Did you get an idea of how I did that? I kept a pointer right here, and I just scanned this list and either put it in the right section or the left section. And now because this list was in sorted order, these lists are going to be in sorted order too. Question. We just look at the X point of each of these points and put it in the left or the right. Question in the back. Okay. Yes. Throw a flag on the play here. So 6 would be right after 8 right there. There we go, 6. Oh, another flag! Holding! Or was that more like a fumble? Yeah, that was like a, okay. This is supposed to be a 6. Problem solved. What we're going to do is scan SY in order to get LY. We're going to use scan of SY and Q in order to get LY and RY. Then we can run this and then we can run that. And then Mohawk, we needed the Mohawk in sorted Y order as well. Thankfully we have it. We have SY right here. We can just go along again, scanning that Y order and seeing again whether it's within delta of this middle line Q, and only keeping if it's in delta. And then once we have the Mohawk set, of course, we do the same thing as we did before. So at this point, I've explained all of the details of this algorithm. Every solution in this class is going to be like this, less than 10 lines of code. This running time is going to be as we described. What I'd like to show you here, URL right here, it's a Java implementation of this algorithm. It's slightly different. They make one slight different implementation choice, which makes it more efficient but more difficult to follow. But this is the crux of the algorithm. If you look at what this is doing over here, this is sorting it by X. They do one extra check, which I omitted here. Our assumption is that all of the points are different. There are no 2 points that are the same. That will mess up our algorithm. So we had to assume that all the points are different. This is doing an explicit check for that. They are going to be slightly more clever. Instead of sorting the Y, they're going to actually do the sorting inside this loop right here, sort of to save a little extra work. But instead of doing the scan that I suggest, they're going to do something slightly different. And then they call closest. And then closest right here, find the median, they compute this delta, they compute this Mohawk, and then they do that comparison. If you want to actually run this algorithm or play with it or inspect its source code, you can do that. Next problem, arbitrage. Our previous example, it did a few things. Showed you how to write an algorithm, showed you how to analyze an algorithm, showed you how many things are like the merge sort structure, showed you how you need a series of insights. Then you come to a problem and you have to solve that problem, and then comes the next problem until there are no problems left and you got a complete solution. And then the idea was from the outside you needed that sorted list of points to help the algorithm. Here the arbitrage problem is going to show the other example, how the problem itself can compute a little bit more information in order to help get the running time that we need. And your homework problem 2 will need something like this. The skyline problem will use an idea like this. So what's the arbitrage problem? This was Apple stock, which I purchased before I came to UVA, which did well. This was another stock I purchased when I came to UVA. This is when I bought it, and this is it today. Not great, right? I'm not good at arbitrage. Now, the arbitrage problem is, and you dream about this, if you could ever defeat time and go back or tell yourself something in time, obviously what you do is tell yourself which stocks to buy in 1987, right? Or when you're born. That kid is born in 1997, so he would miss out on all of the great IPOs, right? What you'd love to do is, of course, buy low and sell at a high point, right? That would be great. Even if a stock like this is an oil company, even if a stock overall goes down, there's still opportunities for arbitrage, for making money, for buying low and selling high. You could have made money there, you could have made money there, there. You could have still become a wealthy person just by writing up. So the algorithmic problem that I'm going to pose to you, we're given an input, an array of n numbers. And our goal is to find index I comma j such that I is less than j, which maximizes a of j minus a of I. So put more succinctly, given an array of the stock prices, the ending stock prices of every day, so given this graph right here, tell me the day that I should have bought and the day that I should have sold, which would have maximized my profit. And let's not pretend like we're fancy traders. We're not going to short sell. We're just going to buy and sell. So the arbitrage problem is, given this list of points, tell me the day I should have bought and the day I should have sold that maximizes my profit. There's an n squared solution, right? Could it be the first day? Try every day, figure out what the profit was. Could it be the second day? Try every day. Could have been the profit. Take every day and try to find its best selling day, compute that profit, and just take the max among that list. That algorithm, just like our one before, is order n squared, right? And the magic mantra is, we want a theta of n log n algorithm. How are we going to do this? How do we approach a problem like this? Split the problem in half. So it's good to have that instinct to just chop it, okay? You can first chop it and then figure out what you need to do and how you put it together, but just chop it. We chop it in half. Good. So in words, we're going to split the problem in two. The structure of many of these problems are going to be first handle the base case and then compute the best trading day where I only traded on the left. I had to buy on the left and sell on the left. Then compute the best trading day if I had to buy on the right and sell on the right. My best trading strategy is either going to be entirely on the left, I and J is on the left, entirely on the right, or what is on the left, I buy on the left and I sell on the right. What we need to figure out is what would be the best trading situation if I bought on the left and I sold on the right. Then we have three things to compare, and you can just return the max of those things, right? This call right here will give you the best opportunity that occurs entirely in the left side. This one will give you the best opportunity that occurs on the right side. The Romeo and Juliet situation, the best thing that you can do is find the smallest price on the left. Okay, so find the minimum of this side right here. And Juliet's going to be the maximum on that side. And so the answer is either going to be the max of ij, I prime, j prime, or Romeo and Juliet. And by max, I mean actually the max of like, does everybody follow? So this is handle the base case, find the best trade you can make on the left side, the best trade you can make on the right side, and then of course the Romeo and Juliet situation is buy on the left and sell on the right. And so you return like this. Let's do the running time analysis of this. How much does that line take? T of n over 2. This line, T of n over 2. This line, order n. This line, order n, right? It's just scanning the array to find the maximum value. And so here we have we have exactly the same thing, which gives us an order n log n solution. Let's not stop here. So we got a solution. And just like in problem set 2, in problem 2, you're going to come to a first solution that won't meet the running time criteria that I put forth in the problem. You need to take one extra step, and this is the idea behind that step. Instead of taking order n to find the minimum and the maximum, I want to try to find a way to do this more efficiently. I want a solution that has this recurrence right here. Notice in our solution, Where does the order n come from? The lines which take in too much time are these lines right here, min and max, which currently are taking order n time. And in order to get a better running time, I need to figure out how to do these operations in order 1 time. So the big idea is that instead of computing these min and max values at this point, let's say that our bit returns both the best trade in addition to the min and the max. The idea is to make our function do more than what was called for. It was only asked to provide the best trade. We're going to make it do something better. In addition to giving the best trade, it's also going to give us the min and the max values. And so let's look at how that would work. Just like before, we can now have the left trade, comma, min left, max left, and we can call that on our bit of half the array. Similarly, on the right side, we'll get a min r, a max r, and we will compute our bit on the right half. And now, all we need to do, return the max of LG, RG, and max R minus min L. In addition, we now have to return the min across both halves. What will the min be across both halves? Exactly. And the max will be. So this solution is now a 3-line solution, and its running time is going to be t of n is 2 times t of n over 2 plus order 1. Because now notice all of these computations are order 1 computations. What did we do? We changed the definition of what our bit has to do. Instead of just returning the best trade, it has to return the best trade and the minimum value and the maximum value. Okay? So we handle the base case as we did before. This is now going to return 3 things like we did before. Okay? Now we recursively call our bit on the left and the right. That's going to give us the best trades as well as the min and max values of those tides. Before, in that algorithm that you see on the right slide, notice I had to spend order n time rescanning the array to figure out the min and the max. In this situation, I received that as a gift from my recursive call. And so as a result, I can compute now the answer as before, and now my job is larger too. I still have to compute the min and the max to return to my parent. And that's where these 2 lines come up. So what did we accomplish? We removed that order n term, and we replaced it with a constant term. Your question is, how do we know that we're returning the right thing? Yes, this right here is the minimum. This is the min and the max of the input array. So recursively, this is going to be the min of the left side and the max of the left side. And so when we compare right here, we're guaranteed that the minimum of the whole thing has to be either the minimum of the left or the minimum of the right. Yeah, buying high and selling low is what I do. So that's not what it's not what you would do. There is nothing else we can reduce.